So the next paper is going to be Voice2Face, audio-driven facial tongue rig animations with cVAEs by Monica Villanueva Ailagas, Hector Anandon Lyon, Matthias T. and Konrad Tolmer.
Hello, everyone. My name is Matthias, and I work at SCA, which is a research department within electronic arts. I'm here to present our paper, Voice2Face, audio-driven facial and tongue rig animations with cVAEs. In this work, we present a deep learning method to generate speech animations directly from recorded speech. So before I dive into the details, I will just show you a brief example. So these are animations that were generated directly from the speech you hear. Sorry, the sound seems to be a little bit low. These videos are also available on our project webpage that we link to from the paper. So what's our motivation for looking into this? Well, the highest quality speech animations today are generated by techniques like the one just discussed, visual performance captures. And such techniques, they create very impressive looking results, but they can be quite resource intensive. So what if we could approximate results like that as a complementary method from a simpler pipeline, such as driving the animation directly from the speech? And that is exactly the goal of this paper. And we specifically have used an approach that is designed to be suitable for both facial animations. So what we mean by that, for instance, is that we don't want to capture the speech style of any individual speaker. Instead, we want a fairly generic looking speech style applicable to multiple characters while maintaining some speech style control. In addition, since we want to be able to put these animations on any rigged head, we also want our method to output rig animations. And then finally, to be able to animate unvoiced sounds, for instance, we don't use any intermediate phoneme or voiceme or no intermediate representations, but we map speech directly to face pose. So when modeling speech-driven animations, it's important to consider that the same speech can be uttered with a wide range of facial expressions. We therefore use a latent variable model for this, where we let the latent space represent variations in speech style. Specifically, we use a conditional variational autoencoder, or a cVAE for short. So what does this look for us? Well, as you know, VAE is a latent variable model that distinguishes between the observed variable A, in our case, all vertex coordinates of the face mesh, and the underlying information that gave rise to that observation, so a latent vector Z. Z is assumed to be standard Gaussian, and you rely on the fact that a function P is able to map that distribution to the distribution of plausible face poses given by the training data. In a conditional variational autoencoder, that distribution is also conditioned by some additional information, in our case, a speech window at time t associated with that animation frame. And since we train our model with data sets of multiple quality levels, we also use a one-hot encoded additional vector Q that represents the quality level of each training example. So during test time, of course, we set this to be the highest quality. In this setting, as you know, we don't train P by sampling a set from the prior. Instead, we also have another neural network, the encoder, that predicts statistics of an approximate posterior distribution of Z given the mesh pose and the speech window. So we train this network with the two standard VAE loss terms, log likelihood and KL divergence, but we also add a third term, which is vertex normal cosine distance loss, with the idea that it might help with surface rotations, for example, for lip rolls. Okay, so on this picture, I want to show you our full pipeline. This is a simplified version, though, so for full details, please see the paper. So our facial cVAE takes as input speech windows associated with each animation frame, and we use standard time frequency representations of speech, such as MFCCs. Within the cVAE, the speech windows are processed first by convolutions to reduce them in the frequency dimension, and then another stack to reduce them in the time dimension. Input from the latent vector to the decoder occurs, or that conditioning occurs in the time in and after the time reduction step. So after training this whole network, we don't need the encoder anymore to generate animations on new speech. We simply need the decoder. However, you might notice that so far we are only generating mesh animations. So to translate those animations to rig animations, we use a separate neural network that we call mesh-to-rig. It's a simpler, fully connected, two hidden layer neural network. And tongue is animated in exactly the same way, but we use a slightly simpler mesh-to-rig for that. The latent vector used for tongue is simple. We found it sufficient just to use the zero latent. But we are a bit more selective for the facial cVAE. So how do we select the latent vector for that? Well, we use a process that we call latent optimization. So this process allows us to automatically find a latent vector that represents the speech style that we want from some example clips. So we first collect a bunch of example animations and speech where the animations have the desired speech style. Then we freeze the weights of the decoder while optimizing the latent vector to give rise to animations of that desired shape. Once that is done, we can, of course, use this latent vector for any number of inferences in this particular model. Throughout this work, we do this to find generic-looking neutral animations, but this method can also be used to imitate other types of speech. So we test our model both qualitatively and quantitatively. In both cases, we compare our baseline model that I just described to a number of ablations. I want to focus on two. The first one we call no silver data. So our baseline data set consists of data of two different quality levels. We have about 45 minutes of high quality data and 90 minutes of lower quality data. In this case, we only train our model on the high quality data set. Now, the next ablation, no quality conditioning, we train our model on both, but we don't use the one-hot encoded vector to disentangle them during training. We also want to compare our model with a state-of-the-art comparable model, so as a reference. So we use another speech-driven animation model called VOCA as a reference. I just wanted to show you what the qualitative evaluation looked like. So we used a user study where users were presented with a picture like this, two animations from two different models, and users were asked to select which one they prefer. We also allowed ties. Tongue was excluded from all of these videos except for a comparison made between the baseline model and the baseline model with tongue. So these are the results from our qualitative evaluation. So we outperformed the VOCA at the 5% significance level, where our animations were preferred in 51% of cases versus 41% for VOCA. Users also preferred animations with tongue, which also outperformed the animations without tongue with significance. We also compared our baseline model and all ablation models versus each other. And I want to highlight one observation from that. So it turned out that the model we trained with just a high quality data set significantly outperformed the one trained with both, but no quality conditioning. However, we also saw that our baseline model that was trained on both data sets, but where we disentangled the quality, did outperform the model trained with only high quality data. So, and as expected, of course, it also outperformed the model trained on both, but with no one-hot encoded vector to disentangle quality. So this observation tells us that adding lower quality data by default deteriorated our results unless we used the quality conditioning vector to handle that. So our quantitative evaluation was based on the fact or the observation that bilabial, so PB and M lip closure is particularly important for perceived quality. So this experiment was done on data for which we both had animations and speech. And what we did is that we annotated this data set with frame-by-frame indications where bilabials were hitting with closed lips. Then we let our models generate animations on the same speech. And by checking if the animated clips from the models were closing the lips at the annotated instances, we could, of course, calculate precision recall as well as F1 score. I should mention, we define closed lips as a positive measure, meaning that recall, for instance, tells us about our model's ability to close the lips where that is mandated by bilabial speech. I'm just going to highlight two results here. So these are the results from 5 training runs with different random seeds for our baseline model and VOCA. We had better recall at 56% with VOCA at 30. However, VOCA did have higher precision, but when summarizing both metrics in the F1 score, that turned out favorably for our model. So to summarize a bit, like comparing the quantitative and qualitative evaluations, we did see partial correspondence, namely that the 2 models that showed the best recall and F1 scores were also the 2 models that had the highest number of aggregate preferences from our user study. So this is an observation that, it could be in line with the observation that lip closure is particularly important. It's not the only factor, but one of the important ones. I want to highlight one other observation too. It's the fact that we did see quite high variance in between training runs, both for our model, but also for VOCA. We tried to handle this both in the quantitative and the qualitative evaluation. But we would like to encourage future work in this field also to be transparent of these variations, because they can affect, your results can vary quite a bit between training runs. And I guess this won't come across too loud either. I'll play it. But this is basically the final video. I wanted to demonstrate how tweaking the latent with the same model can change the speech style or expression of the animation.
It was the time of year when the ground is carpeted beneath the furnace with brown needles.
There, where he was appointed by his superiors to give lessons in philosophy, the young novice had from the first to battle against the defects of a voice that was both harsh and weak.
Okay, so to summarize, in this paper we presented Voice2Face, a model that generates both facial and tongue animations directly from the speech signal. We showed how we can find a way to automatically select a latent vector that gives a desired speech style. We showed how we could use quality conditioning to improve on our baseline results with datasets from multiple quality levels. And since our method produces rig animations, we find it suitable for both facial animations in, for example, game productions. Thank you very much.
Yes, thank you very much for this talk. Are there any questions in the audience? Yeah, you can just ask and repeat it.
Okay. So I guess the question we can ask in when you have like a method that relies on data is how does it extrapolate, for instance, if to another language or another like culture or
that's a good question. Sorry, did I cut you off early or no? Okay. Now, I think there are several parts of this in terms of like, if you think extrapolating to different people, I mean, we all have a unique voice, even if we speak the same language. So our method there is that we trained our model on as many speakers as we could. And we tried to find speech representations that were as generic across different people as possible. When it comes to different languages, for instance, it's also a question about like we used speech representations that, from my understanding, are fairly standardized across, like, for if you study like speech recognition across different languages. But another approach could be, let's say you use a phoneme extractor instead of MFCCs, say, then you could work in a little bit more dependence on the language for which your phonemes are, or your phoneme extractor model was trained on. So I think it's a little bit of a, you have to design this depending on the application. And you can, depending on those design choices, you might limit your model more or less. Did that answer your question?
Okay.
I have a question.
Hi, thanks for your presentation. The question is related with your cVAE.
Yes.
So in your encoders, you get the Z from the input and the conditioning on the speech.
Yes.
So in my understanding, can we regard the speech as a sequential data? And in your encoding step, I found you got the A at timestamp T. The A height is sampling from the input AT and the speech T. But what if timestamp T+1? So do you also consider the temporal dependencies? Yeah, this is my question. I'm not sure.
No, I think if my understanding is basically you're wondering, are we not doing, because our model is fairly, it doesn't have a long-term temporal coherence in that way, and your basic question is if we're not missing anything with that. Is that correct? Yeah. So different papers in this field do this a little bit differently. In our case, we found that we didn't need to build like an autoregressive model or something like that to have fairly stable, or as stable as we wanted to temporal coherency. We have some tricks that we use, is that when we sample a latent during training, we use that latent to predict 3 consecutive animation frames to encourage a latent to be basically more long-term stable. But those are like small things, and we found that above that we didn't need anything in particular.
Hello. So I got, if I'm understanding correctly, the encoded vector space concentrates mostly towards the eyes and the mouth, right? So if I think on the other parts of the human face that is also really that can contribute a lot to the expression, like maybe the nose flaring or blood rushing to your face and coloring your face to show the emotion, heightened states of emotions in particular.
That's interesting. I mean, our method is we're just trained on like vertex positions for the cVAE model, so it wouldn't learn anything about differences in texture. That sounds very interesting. Maybe you can train a separate model to like learn when a person is blushing or not, but I do find that, or we did find that people speak with their own way, even if we don't think about it. Someone might pull their lip up a lot when they talk, and things like that is possible to see in the latent space that we can sort of, and that's why we wanted to combine many speakers and then try to find something generic. So yeah, I think there are some aspects of this that we catch and some that we don't.
Thank you.
Thank you.
I was wondering if you method the voice speech, or this is just to show some results at the end. Automatic, or this is
Sorry, it was a little bit hard to hear for me, but you mentioned emotion detection, right?
the tone,
Tone.
like the tone.
Tone.
Automatically.
Right. I mean, I think it will depend on how much of that falls through the our speech representation. And I think the 0th substrum of MFCCs is like the total. Okay, that's energy, but I think I can't see that I've observed a great difference between like a high pitched and say a low pitched speaker in our results, which I guess that would mean either that we have those variations in our training data, or that it doesn't fall through or it's being filtered away when we process the speech. I don't know if that answered your question. But...
Just about issue. Maybe future work. Well, maybe future work.
Yeah. One thing I would say is for future work, we would like to, or one idea could be to see if we could detect things that are not associated with just like neutral speech, but let's say, you know, emotion detection, and from there apply different expressions. That would be a cool application. Thank you.
Okay. Then let's thank the speaker again. Our next paper.